Okay, so on page 4, I asked you to go ahead and, it's a blank sheet of paper. Go ahead and break up that sheet of paper so that we have a column for summer, a column for winter, and a column for spring and fall.
Spring and fall don't matter.
Well, spring and fall, you're gonna see, that on paper, they're actually very similar. So I would like you to write down what you know about spring, winter, summer, and fall. So actually, I should say summer, winter, spring, and fall. What facts do you know about each one? Page 4. So go ahead and do this for a couple minutes. What you know about summer, winter, spring, and fall.
This is blank one.
Yeah, it's a blank one, so make it look like this. Yeah, so obviously we could start with temperature. Take it further than that, though. So hopefully you can add more than just the temperatures for each season. Hopefully you have experienced enough summers in your life, enough winters and spring and falls to be able to tell me some of the differences between the seasons. It's blank though, so let's get going.
Well, at least there's straight on.
And they're nice and straight, right?
Yeah. What are you doing tomorrow today?
I was probably going shopping. Like a girls' night day thing.
So cute. Maybe I'll do that too. And then my mom can buy me stuff.
Well, yes, that's probably how it will end up.
Maybe I'll buy her lunch.
Yeah, I mean, my kids don't, the only money my kids have are the money that I give them, so there's no need for them to buy me lunch.
Wow. Never mind.
Okay, good.
I don't know what I'm doing for Mother's Day.
Okay, and then we'll get started, yeah.
I'm a mother.
Opening my swimming pool.
Ooh. Good day.
We're ordering a new pool liner and redoing that.
I don't have a pool, so,
You should get a pool.
yeah.
We're going to see Brooks and Dunn, I guess, and they just texted in the group chat. I don't listen to them, but I guess we're going.
Okay, all right. Anybody else have any fun adventures they need to tell us about?
Yeah.
Okay, what do we know about, give me some of your facts. I'm going to call on some people. Okay, Felicia, give me one.
The northern hemisphere is from.
Oh, you just observed that?
No, but I know that.
Okay, I want to know about facts about the season.
That is back to my.
No, that's not what I'm, Carter, give me one.
I know.
Okay, so we got different color leaves.
I know.
Okay,
That's in the fall.
okay.
There's no leaves in the. I could just list off the ones that I think great summer.
So I can.
Oh, okay, so guys, I'm asking, so one example that I was looking for is that it's cold in the winter, right?
I put that down.
Okay, everybody put that, it's cold in the winter. What else did you add?
Warm in the summer.
Warm in the summer. Can we actually even just put hot in the summer?
Yeah.
Hot/warm.
Plants fully grown. In spring and fall.
Sunny.
Yeah, it's mid. Okay, mid. Now, you say it's sunny, but isn't it sunny? Aren't there sunny days in all three of them?
Yeah. Sunny days in the winter too.
Yeah, there are definitely sunny days in the winter too. So what about, okay, there's a higher UV index. Daylight hours, when? What about them?
Longer in the summer.
Okay, so long daylight. And what else? Short daylight here?
Yeah.
Sorry, you just keep saying it.
And we got mid hours here. So what else did you say? High UV index. Mr. D, do you mind looking up exactly what the UV index is?
Probably like
I think
six.
like a seven.
No, like I want to know the actual, because it's not something we talk about in earth science.
Yes,
Isn't it like the amount of like sun rays?
I think
Like,
it's
yeah.
connected. I'm just
Um,
checking.
if the UV index is like 6 or 7, it's like perfect for tanning. Anything above that, you'll get burned.
Is an international standard measurement of the strength of the sunburn producing UV radiation.
Okay, so,
We wanna know
so,
the actual.
so, no, that's exactly what I wanted. That I wanted to know exactly what it was. So it's how they measure the strength of the sun. In earth science, do you guys know what word we use to talk about strength of the sun? Well, yes, it's directly connected to the angle of insolation. So a high UV index means you're going, the higher it is, so Sarah just said, would you say 6? Higher than 6, you burn. Around 6, you're going to kind of get a slow tan. So I believe, because my daughter was hung up on this yesterday it was a UV index of 5, according to her.
It was like a 6 or 7.
Okay,
It
so,
was a 7.
so what, yeah, so we were looking, it was about 4 o'clock when we were looking, so it might have
Yeah.
gone down. So the higher it is, the easier you're gonna burn or tan. The lower it is, so there's a low UV index,
And that's why we're all pale ghosts.
and that's why so higher the UV index, the easier we burn.
Good.
We call it
Mid.
the higher the index, the easier it is to burn. So in earth science, we call this, it's most intense. So the sun is most intense in the summer, least intense in the winter. And then mid intense in the spring and fall. And then, Zach, why did you say it's the highest intensity or the highest UV index in the spring or in the summer, sorry? Yes, this is because the high angle, it's called high angle of insolation.
And you can observe that, Miss Ray.
And you can observe that. You can go out. What did we discover? We were just out for Wellness Wednesday about a month and a half ago, and then we were just out earlier this week.
No, we won't.
What did we notice about where the sun was in the sky on those 2 different days?
Up.
But where was it compared this time compared to the last time? So, yeah, so sun is higher in the sky. Oops, so that was, we did the summer one. In the winter, it's going to be a low angle.
Good.
And a low angle of insolation because it's going to be, sun is low in the sky for the winter. And then, yeah, it's gonna be a mid angle
Yeah.
and a mid height in sky.
Making that all the ones on the spring and fall, the same way.
Yeah.
Any other fun facts that we know about the sun?
The sun is hot.
Sun is hot, but that's,
Yeah.
yeah, but that's not what I was asking. So I was asking, so differences you might notice in the
It
winter.
rains during the
So
spring.
I specifically do want to just talk about the sun, so I guess I should have
Oh.
cleared that up. So that goes along with the leaves we were talking about earlier, and, okay, it's not true, that's not it, yeah, that's not it. Technically, we're closer to the sun in summer,
Yeah. was farther away in the winter.
I lied, we're closer to the sun in winter than we are in summer. Yeah. Yeah, I feel like we talked about that already earlier this week,
Yeah,
but
we did because like,
We did.
I don't know.
we did.
Oh, yeah. that's
Yeah,
right.
the sun, we just so happen to be closer to the sun during our winter. So, spoiler alert, that doesn't cause seasons. Seasons are not caused by how close we are to the sun.
What if you put it like, what if the earth was like almost touching the sun? Would that affect the
No.
season?
Well, yeah, then it might not affect the seasons, just might affect Earth. We'd be hotter. So I guess what we have to discover is what will make us have hotter or warmer days in the summer that are longer, the sun's most intense, giving us that high UV index. Why do we have a higher angle of insolation, and why is the sun higher in the sky in the winter? Look, all of those are opposite in the, oh man, it's gonna be a long day. So
Yeah.
why in the summer is it hot, long days, most intense, and then cold, low in the sky in winter? And then why is everything mid in the spring and fall? So it has to do with three things, or actually three things that will cause us to have these different seasons. And as some of you already discovered, right on the next page here are the causes for those, or the reasons for the season. Come on, let's say it all cool like that. Reasons for the season. There's three of them. And there has to be all three of these reasons. They have to be true for us to have seasons. Without just one of these, we would not have seasons. So what I have set up in the back is what looked like it's a model of, not the whole solar system, it's the Earth and the sun and the moon. We're gonna go back and we're gonna look at that and see what's going to cause us to have the hotter, longer, more intense sun during the summer. Some of this you might already know it. If not, you're gonna learn it. If you unfortunately do have to watch the video, of course, it's not going to be quite the same. But hopefully you can still hear me while I'm describing stuff and you can relate it to this picture here. So those of us in the classroom, let's go back to that back table. We're gonna talk about treatment for the season.
Whoa, that rhymes.
I know, it's like I'm Dr. Seuss. I didn't even know it, Jeff.
No, that's not it.
No, it definitely isn't. All right,
You're so freaking cool.
I know, thank you for acknowledging it. No, come closer, everyone. So you can see, all right. Be scared, don't be scared. All right. So what we have here, as you can see, we have the Earth. It goes around the sun. It's this cool model thing. Everybody always expected to go on its own. But I looked up, tried to buy a new one of these that did go on its own, and they're like over $500. Even this guy right here is like $500. So
Then what's the difference?
so we're not getting a new one. We'll just move it by
I just saw
myself.
that one.
No, I like it. Yeah, I thought the other ones were over $500. So here we go. We got the sun, the Earth, yes, the moon. We're gonna ignore the moon for this lesson. We're gonna talk about the moon the next couple of days. All right. So first of all, you notice the Earth is tilted, right? We talked about that. That's not a mistake. It's supposed to be tilted. That tilt, without the tilt, we would not have seasons. Why, Jeff? Why? So what did we already say we know about summer? Hot and long hours of daylight. And the sun is higher in the sky, creating more intense sunlight rays. So let's take a look at here, which if those of you who can see, I have it set up so that we're in June. That this would be June 22nd, maybe June 21st. And so what I want you to notice, take a look at where the sunlight is hitting the Earth.
Oh, it's sitting there.
Okay, it is hitting, so what I want you to focus in is, look at that North Pole. What do you know about where it is right now in the North Pole? It's in the sun. Now, every day, what does the Earth do? It spins, it rotates. So there's no way for me to do this on its own, but I have to do it. So I'm gonna spin it. What do you notice about the North Pole and spinning? It's staying in the sunlight. Sarah, you can see the south pole pretty good. What do you notice about the south pole? Sun, not even that much. It's not hitting the south pole at all. So in this setup, where I have it set up in June, if you spun the earth from the north pole, just like you would like a top, like just spin a top, that north pole does not leave the sunlight. The south pole does not leave the darkness all day long. So that means on the first day of summer, the north pole is experiencing 24 hours of daylight. The south pole is experiencing 24 hours of darkness. In addition to that, let's talk about us, because, well, we like to talk about us, right? Us in North America, us in Buffalo.
Feel like story time.
Does it? I would like you guys all closer. No. All right. So not just the North Pole getting a lot of sunlight, let's take a look at the South Pole. No, now let's look at the dot, which is supposed to represent us in Buffalo. So right there, Buffalo is just in the darkness. Right over here is the dot, for those of you who can't see. Now I'm going to spin it. Pay attention, especially you guys right here who can see. See how much sunlight that dot gets? See how short it's in the nighttime? That's gonna be like those long summer days. We're getting closer to them now. You guys notice that it stays light out really late? The sun is up really early because we're getting close to this day where the sun is, where we're getting, where the sun is just like it is here. Carter, how much of the earth is lit up? Half of it. Half the earth is lit up. Does everybody see that it is, half of it is light and half of it is dark?
Oh, yeah, probably.
But what do you notice? Is it cut down straight from the North Pole to the South Pole? Nope.
Nah.
If it was cut down straight from the North Pole to the South Pole, then we'd all experience 12 hours of daylight, 12 hours of darkness.
That would not be good.
No, wait, let's go to this position right here. Now what do you notice, Jeff, about who's lit up and where the light is, where the dark is?
It's probably right there.
It is right there. It's right there. Half of the earth is lit up, half of it is dark, just like before, but now in this position, it is straight through the North Pole down to the South Pole. It's like I took a knife and just cut right down and this half is lit and that half is dark. It is kind of like science. Yeah, what day is it? Is there a day in the year? No, that's not it. This September.
Why?
It's really September. It's supposed to be September 21st in this setup. What do you guys know about September? What happens in September?
You go back to school.
You do go back to school. What season is it?
Fall.
It's football season. Oh, yeah. Yes, it's fall. I like it.
Football season.
All right, I like that that's how you associate it. But yeah, this is supposed to be the first day of fall. You guys should, anybody know what the first day of fall is called?
Nobody knows.
An equinox.
Oh.
So by the way, you guys are all going to have to know that after Monday.
Right.
This is an equinox. And it's called an equinox because everybody is equal. Everybody in the world right now will receive 12 hours of daylight and 12 hours of darkness in this position. Let me just quickly switch over to March 21st. Now, those of you over here, what do you notice about the daylight? Split again. Half is light, half is dark, going dead smack down from the North Pole to the South Pole again. Also known as the spring equinox. Again, everybody's equal. Why is the first day of summer not called an equinox? It is a solstice,
Equal.
because it's not equal. Okay, so in the summer, and then when we come over here to the winter, it's no longer equal. You can see in this case, the northern hemisphere, and especially the North Pole, is receiving more than that 12 hours of daylight. Let me bring it over to winter. Now, what do you see about where the sunlight is hitting in this winter season? Okay, the south pole, those of you who can see the south pole. If I was to spin it, Destiny, what do you notice when I spin this about the south pole right here? Still there, it's getting 100% daylight. Kathy, what do you see about the north pole when I spin it? It stays dark at the north pole. What? No, let's ignore the military today. It does do that, yes, there are times when it does that, that's gonna be an eclipse. So we'll get to that next week, but. It was pretty interesting colored, I don't.
What day?
Yeah, it was,
What day?
it was earlier this week, it must have been. Okay, back to this.
Okay, you spin it, so it's
Okay, let's get that in a second. So first of all, again, remember how it's dark? We had said we had short daylight hours in the winter. Here's why. North America can only be in the daylight for this little chunk of time. So this is what's gonna give us those short days when it's still dark out, when you get on the bus, and then it gets dark again by like 4:30 in the afternoon. Yeah, some of you, it's when you get off the bus, like some of you never get to experience daylight, in the winter. Yeah, cause it's cool. Okay, if we were in the North Pole though, what would be happening at the North Pole? No, not in this case, you would be standing, there'd be no sunlight.
Also be working right now.
Yep, 24 hours of darkness here in the North Pole. Now, remember, we were talking about the UV, oh, wait, we were talking about the UV index. You guys are saying it's starting to get high, which UV index, like I was saying when we were talking about it, is not really an official earth science term. It's nothing that we're gonna talk about in earth science in the Regents level at least. But we talk about it as being more intense. So instead of having a high UV index, we say it's, the sunlight is more intense in the winter or in the summer. What, geez. What does intense mean to you?
crazy.
Stronger. It's going to, basically the sun is stronger feeling, means you will burn faster. And then like Zach said, it's because the sun is hitting you at a higher angle in the summer. So again, let's imagine the sunlight shooting out of the sun. See how that 90-degree angle with the ground is right in this general area? Again, it hits right directly there. So that's a higher angle. The sun will be higher in the sky in our June than it will be in the winter. If we go over to the winter, it's hitting not at a 90-degree angle up in the northern hemisphere, something smaller. So as one of the reasons we have seasons is the tilt. What would happen if we didn't have the tilt?
There would be no season.
Great, there would be no season because everybody would be receiving the same amount of sunlight, just like we do in our spring and our fall. So everybody would be mid if we didn't have that tilt. Wouldn't it be sick? So it's not the best example because the sky's a little bit, obviously a lot bigger than that globe. But without the tilt, so if I make it so there's no tilt, and again, it's not gonna light up the same way because it's too big. But in this case, where there's no tilt, what used to be our summer, now everybody's getting that 12 hours of daylight, 12 hours of darkness. Well, would it be cold then? It wouldn't be hot then. No, it would be
Man.
mid.
How about, I don't like that, I want it to be hot.
So in that case, the equator still would be hot. If we weren't tilted, the equator would still be getting the highest angle. That's where the sunlight would be hitting at the 90-degree angle. We'd be getting where it'd be kind of in the mid area. So it wouldn't be high, but it wouldn't be low. It would be like spring and fall all year long. Depends on your personal opinion. I think. So one reason we have seasons is our tilt. Without the tilt, we'd be stuck in spring and fall all year long. Everybody would be. So now let's talk about, okay, so yes, we're tilted. What's another reason we have seasons? What's one thing I just had to do to this to make it be different seasons? Whoa, careful there, Keisha. It's the revolution. Right now, if the world stopped revolving around the sun in this position, what would happen to us?
It'd be cold.
we'd be cold all year
Yeah,
long.
no way.
So luckily, the earth does revolve around the sun, putting us in those different positions to get the sunlight, different hours, different angles. So one reason is the tilt, another reason is the revolution, and the third reason is one I'm guessing you're not going to get. It's called the parallelism of Earth's axis, what you hear in parallelism. You hear that parallel part. What it means is the axis stays parallel to itself no matter where it is. My best way of explaining it is, see how the North Pole is pointing basically to the back of the classroom here?
Yeah.
Which right now just means it happens to be tilting towards the sun. But let me put it over here. Is it still pointing towards the sun, the North Pole? No, but it is still pointing to the back of the room. In fact, it's at the same exact angle it was back there. So the Earth here, the axis here, is parallel to where it was here. Keeping it going. Again, is it pointing towards the sun? No, but it's still pointing to the back of the room. Same deal here, not pointing towards the sun, but still pointing towards the back of the room. So the axis always points the same way, because if it didn't, let me show you what would happen. So here where the Earth was leaning towards the sun, again, the North Pole getting more daylight than the South Pole. Now if I make it so it doesn't stay parallel, see how that would have intersected here, so it's no longer parallel here? Still is going to be our summer if we didn't stay parallel, but we stayed parallel. So it does not revolve around the sun, always pointing at the sun. It would be kind of weird. It does always point the same spot. In fact, it always points north. So without that parallelism, we'd be stuck, if we were stuck pointing at the sun, we'd be stuck in our summer, which yes, Felicia would be happy, but Mrs. Riggs would not be, so, yeah. Yeah, no, not my idea.
If we had summer and fall, that'd be great.
Yeah, but I was thinking, like, let's do mosquitoes. What if we had mosquitoes if we were always in the summer? They'd be constant. What about like those big ugly bugs that get killed by our snow, like cockroaches? Do we have many cockroaches here in Buffalo?
Yeah, they go.
No, we don't have cockroaches. Yep, they have to be somewhere where they can survive. through the winter. Even fleas are sick.
Why?
I don't want monsters, so, all right, let's go get this stuff into our notes and then we're pretty much done for the day, except for going over our homework. One other thing that I want to tell you is, one thing you're going to have to do is if you see a picture similar to this one that I have on the board, you're gonna be given one of these minus the labels. So it'll just be a picture of the Earth going around the sun. One thing the Regents will make you do is label which one of these is spring, summer, winter, and fall. I have a good explanation for how you can do this. The first thing I do want to point out is this drawing is really representing that model. So in this case, it makes it look like the Earth is going around the sun kind of in this plane. So this way, if this was the sun, it kind of makes it look like it's doing this. Keep in mind, it's not. It's really doing this. So this one is when it was out in the spring and the fall. So it's not really pointing at the sun here. You guys it's been nice these past couple of days, right?
Yeah.
What have you noticed about the people of Western New York? Everybody's been outside. The second it gets nice out, we go outside.
There's more stuff to do.
Because there's more stuff to do. I kind of like to think of that as soon as that sun comes out, we start worshiping the sun. We get out there and we're like, heck yeah, it's here finally, thank goodness.
Oh,
And then it goes away and everyone's like,
And
oh
then
my
we're
God.
sad and seasonal depression kicks in again, but that's not the point. I use that phrase, sun worshiper.
Oh.
When I think of worshiping, a lot of people will then pray, right? And when people pray, they tend to bow their head. I want to focus on that bowing.
Oh, like the earth is bowing.
Yes, does it kind of Look, in this case, that the earth is bowing to the sun here, like a
yeah,
sun worshiper in summer.
Yep.
That's how I figure out which one of these is summer, is by looking to see which one is bowing towards the sun, worshiping the sun almost. So this guy is winter, or sorry, this guy is summer. The one that is bowing towards the sun is always summer. Don't get stuck on it's the one on the right. Because one thing they could do is, instead of having the world tilted this way towards the left of the paper, they might switch the globe around and have it tilted the other way. In fact, they absolutely will do this. Just messing with you. So don't get stuck that summer's always on the right. It's whichever one is bowing to the sun is always summer. So in this case, we've got the one here. So what do we need to write about the tilt? There we go. So the tilt, yeah, I think I might have screwed up the notes. I might have combined them. Give me 1 second before you write this. Let me find exactly what I wanted you to write there. Oh, 3, no, 5, no, sorry. But don't write this yet. I think I screwed up. Yeah, I did screw up a little. We'll just go with, I'll write it out. So right here on page 5, the earth is tilted. So first of all, there is a tilt. It is tilted. Does anybody know how far it's tilted?
3.5.
It is 23.5 degrees to the north. It does always point north. What that tilt does is causes different latitudes to have different amounts of daylight. And then one thing we know is more daylight will equal warmer temperatures. Yes, yes, sir.
15.
Yeah, that's not counting today. So counting today, it's still 19. All right. What do we need to know about revolution of Earth? Is that, or revolution of Earth around the sun? It just means, and hopefully you know this, Earth goes around the sun. Yeah, I think I said, hopefully you already knew that one.
Yeah.
And then again, what does parallelism mean? It means that Earth's axis does not change directions. So Earth's axis does not change direction. It always points north. And once you're done with that, turn to your homework and we'll go over last night's homework, which was on pages 18 and 19. Go ahead and write that and then flip to 18 and 19.
Was there,
19.
I turn mine in Monday,
Yeah.
and then
Okay. Ready for 18 and 19? So I know we started to talk about questions 18 and 19 at the end of class yesterday. Who remembers the first thing I said about 18 and 19? You gotta read. I know so many of you would see question 8 and just start here. But without reading these 4 lines of questions up here, or 4 lines of words, question 8 might not make much sense. Maybe you'd be able to figure it out. Maybe you would have read it and then be like, I don't know what it's talking about. And then maybe you would have read the directions. But guys, the #1 rule of earth science is to read all the words. And it's that for a reason, because here's some important information about this.
There it's at mine.
You guys done? Okay. All right, so again, remember that eccentricity is, what's the formula and where do we find it?
It's on the first page of your reference table.
Okay, so guys, I don't ever expect you to memorize this. It's right there on the first page. So it's distance between the 2 foci divided by length of the major axis. When you did the reading, they told you this was planet D revolving around a star. So here's the star and they label the other focus. So remember, the 2 foci are those 2 marks, the star and the other one is marked there when I did my math. I did 2.5 is the distance between here and here. Do you guys agree with that or really close to it? And then there was some discrepancy period too of what the major axis is. Where do I measure to find the major axis of this planet D? It's all the way across D's orbit. So here's D's orbit. This entire section from there to there, so there to there, is the major axis of D. When I measured it, I got 7.9, which gave me an eccentricity of 0.316. Now remember, we're not all going to be the same. Did that answer question 8 though? No, because it wants you to describe the eccentricity of D's orbit relative to all of these guys. Now, can you tell by looking at them that they're different? You got to go to your reference table. Page 15 tells you the eccentricity of Mercury, Venus, Earth, and Mars. Mercury, Venus, Earth, and Mars. What do we know about this eccentricity compared to D? Okay, D is more oval. That could be a perfect answer. Oh, D here, so D's orbit is more oval.
I put less circular than that.
That's perfect too. So anything that means this, you could have also stuck with just the numbers. You could have said D has a higher eccentricity than the other planets. What do we say about for number 9? When we got to be sure to describe the force of gravity is the greatest and where is it the least? Where do we know it's the greatest? When D is close to the star. When is it the least? Least when far away from the star. Just a fun fact you got to know. Gravity is strongest when it's close to the star, so that would have been over here, and gravity is weakest when it's far away. When you did the math here, you should have gotten an eccentricity of 0.7 for number 2
Oh, yeah, I got that.
and 0.68 for number 11.
Oh, yeah, I got that.
On this side, what do you say for the actual shape?
Oval.
Oval would have worked. Did anybody say anything different?
Oh,
You cannot say it's a circle
I'm not gonna say, I didn't know that one weird.
because there's another answer.
I don't know that one weird word you said for it.
Ellipse.
Yeah, that, I don't wanna say that.
Okay, those are the actual shapes. You could have said a slightly squished circle.
What?
So you'd have a circle and then you squish it to make an oval, but it is not acceptable to say it's a circle. You could say it's almost a perfect circle, but it's not. I think I told you you could have skipped 13, but yes, it is winter. So it is, oh, what does the word perihelion mean?
It means.
This is when we're
Close.
close. So we are closest to the sun during our winter. We will emphasize that again, starting more on Monday. What happens to the apparent size of the sun as we move from perihelion, which again is close, to aphelion, which is far away? What happens to the apparent size of the sun?
Bigger.
When we get farther away,
Oh.
it will
Oh,
look
it will look smaller, I mean,
smaller.
I almost got 100.
And state the relationship between distance from the sun and the orbital velocity. What happens when we're close?
Or we're supposed to set it moves faster than we.
So when we're close, it moves fast. When we're far away, it's slow. And in this diagram, it wants to know who is receiving the greatest intensity. That would be right here where the sun hits at a 90-degree angle, and that is the equator, answer number 1. So no homework tonight. We're gonna continue on with seasons tomorrow or Monday. Remember, anybody who's doing test corrections, they are also due on Monday.